Good morning, everyone. This is a e-learning for this Thursday's lecture. We will have two parts. First of all, we go back to the lecture 3 notes to go through the main points and then talk about the uncovered content on how to use the linearization methods first. And then we go to the second set of slides uploaded on FALE about the state space modeling approach. First of all, recall we studied in the earlier lecture, the Laplace transforms is a new type of techniques that can help us to solve a series of ODEs. And then we use the transfer functions to express dynamic models with a lot of nice capacities. So first recall what is Laplace transform. It turns the time domain to the Laplace domain, S domain, through this unique transformation. Also, the inverse Laplace transform is able to turn the S domain back to a time domain. It's very important that both Laplace and inverse Laplace transforms are linear operators. Therefore, they follow the linear combination laws and have nice features for calculation. And we show some common functions, what their corresponding forms for the Laplace transform. These are very commonly used, including the constant function, step function, derivatives, first order and higher order, exponential functions, rectangular pulse, impulse function. When they need to check these Laplace transforms, they can always use the table in the textbook to see these existing transforms and use them directly. And then this technique can be used for solving ODE functions. Let's see this equation of ODE. Then we take the Laplace transform on both sides. Then we from the inverse transformation of it to get the solution of yt. So this is straightforward way if we can directly use a table to find the Laplace transforms. If not, we can then use the partial fraction expansion method. So first turn the Laplace transforms to work on the original ODE and then use the form to do a PFE in order to get the individual terms to be summed together with these coefficients that can be evaluated using the Heaviside expansion method. So this is a PFE approach to give us the corresponding Laplace transforms. So general idea here is just to turn the time domain operation, time domain ODEs, to the Laplace domain. Because we got a lot of nice features, we can use the corresponding forms of the solving strategies directly, and then use inverse Laplace transform to turn the Laplace domain back to the time domain and get the solution yt. Some important features, we talk about the final value theorem about when t goes to infinity, we can use S domain to evaluate its extreme value, final value, and the time delay described as theta and in both domains. Then we introduced the transfer function models, which relates one input to one output. So definition makes it a linear format. We define the deviation variables as the value of the variable minus nominal steady-state values. Therefore, this deviation variable always has a zero initial condition. That is a nice feature to make the calculation easier. This example is the same as we discussed in the tutorial, the stirred tank heating system. So you can see the equation procedures as we discussed earlier. there was a typo in the original code. So this equation 8 here should be a plus then, because we define the new deviation variables, but Q prime follows here. Recall that we take the Laplace transform of the energy balance format here. So we got this whole equation on the S domain. Only this T prime initial condition is a deviation, so this term is 0. It can be reduced. And the other term can be further rearranged to form the specific format. Okay. After rearranging the equations, we got a nice format, similar form as we discussed in the tutorials. So we define the new variables of the system to simplify the impression. And then the transfer function between two variables, one input, one output, can be obtained for T prime over Q prime or T prime over Ti prime. Okay. And we also talk about some properties of transfer function models, including firstly the steady state gain. So this is defined here as a K to be a constant for the linear system. And this can be solved using the final value theorem to get the steady state gain. So we define the order of the transfer function model to be the order of the denominator polynomial. Some nice features include the additive properties, so two transfer functions can be combined together, as well as a multiplicative property. So if they have operation in series, so additive is a parallel format, they can be added together. The multiplicative is a in series structure, they can be multiplied together. Okay, that's the basic summary for what we have discussed. And then we move to some new content. We define initially that a transfer function models need to be linear between the input and output relation. If this model is nonlinear, and it's true that many real processes, most physical processes, and the physical models are nonlinear by nature. So we need to conduct some techniques to linearize the model first in order to transform them into transfer function models. This is also feasible because over some small range of the operating conditions, the behavior can be like nearly linear over this small range of conditions. So linear approximation can be very helpful, especially just for the analysis. These linear models can be obtained analytically by a method called linearization. So it is based on Taylor series expansion of a nonlinear function about a specific operating point. So two important points here are to conduct a Taylor series expansion based on a specific operating point. So let's have a look of how to do this. If we consider a nonlinear dynamic model relating two process variables, which are the input U and output Y, and the system has the dynamic behavior dy over dt to be a nonlinear relationship with respect to U and Y. If we perform a Taylor series expansion about U bar and Y bar, so we need to select this operating condition U bar and Y bar, and then conduct this expansion. We only consider the first order terms here and neglect the higher order term. So first evaluate this f function and then evaluate the first order derivative to u multiplied by u prime, and then the evaluation of the first order df over dy multiplied by the term y prime. So here this prime term u prime is defined as u minus u bar, y prime equals y minus y bar, and the subscript s denotes a steady state value, which is a u bar y bar. So here the partial derivative terms are constants because they have been evaluated at the nominal operating point, steady state point already. So they're just actually constants or just some numbers. So you can directly write the function here. The y over dt dynamics can be described using the format. Because u bar y bar is steady state, so the dynamic term, because f is a dynamic change dy over dt, the dynamic term at steady state equals 0. And also because this deviation term is defined as y minus y bar, so the dynamics follow the same pattern. Dy over dt equals dy prime over dt because y bar itself is a constant. So these two deviation terms, derivative terms, are the same. So if we substitute b and c into the equation A, we actually get the linearized model already. So it's d prime over dt equals the function value evaluation, this is constant, multiplied by y prime, plus this constant multiplied by u prime. So this is our linearized model we can further use for the analysis. Let's have a better understanding of this based on the next example of the liquid storage system. If we just consider the mass balance of the system to have the dynamics of the heat, H, changing with time, multiplied by the area of A here. So the dynamics of the change of the volume will equal to the flow rate Q in minus Q out. And here it has the vol relation of Q corresponding to the coefficient, the constant CV, the vol constant, multiplied by the square root of the heat H. So this is the experience equation defined here about vol. Then if we combine A and B, 1 and 2, those two equations, and rearrange it, we got the dynamics of dH over dt. We define this as FHQI because these two are the variables and they are nonlinear functions because of this square root here. Okay, so if we want to use our linearization methods, as we just discussed, use this format to linearize the model, we will directly use dH prime over dt equals evaluation at steady state multiplied by these two deviation variables. So this is overall linearized model. Because here the steady state derivative evaluation can be directly obtained from the f function, so just conduct the first order derivative and evaluate the steady state value. We get this constant from these two equations, and then take them back to the linearized model equation 4. We will be able to get the overall model that can be expressed in terms of a vol resistance. We define this new term, new parameter R, to be 2 square root of h bar over CV. Then we can express a whole linearized model using just the area A and the vol resistance R. So this is our linearized simplified model. Okay, so following the linearization step, we have then described all the steps to get the theoretical model of the transfer function model of the chemical process. So firstly, we introduce for the dynamic process models, we always start with differential equations. We want to obtain a steady state model by setting the derivatives to 0. Then the nominal steady state conditions are specified. If this dynamic model is linear, then the steady state equations can be directly obtained to get the deviation variables. But if the dynamic model is nonlinear, we then need to this additional linearization step to use Taylor series expansion to linearize around the nominal steady state. Then we move to step 3. We can express the model in deviation variable form now. It's perfect to take the Laplace transform because we have initial conditions are 0. And then it's a solving process we discussed earlier to use the repeated process to eliminate the output and rearrange the whole function to get the final transfer function. Okay, so this is a general procedure to develop the transfer function models. Just now we have discussed the transfer function models and some linearization techniques. The next content of this lecture is to introduce you the state space models. This is quite advanced part but it's very important for process modeling and control. This may not be the core content in this module, but I would like to introduce you what are the state space models, SS models, because this is the foundation of many advanced control strategies. Okay, so let's use a new e-learning slide to have a look of how we derive these new type of models. So normally dynamic models derived from physical principles consist of one or more ordinary differential equations, ODEs. In this section, we consider a general class of ODE models referred to as state space models. And here it just shows some standard form of a linear state space models. It's basically have a variable x and take the derivative x dot equals the matrix A, B, E, C here are all the matrix of constants, made of constants. So those AX B plus BU plus AD makes the x dot term, while y equals cx is output. So let's have a look at what these variables or constants mean. So x is defined as a state vector. It's a state. So x prime is the derivative of the state dx over dt, the state vector. U is a control vector of manipulated variable, also called control variables. So U has a coefficient of B. And D is a disturbance variable, disturbance vector. So we have E before disturbance vector as a coefficient. In the second equation, Y is the output vector of measured variables. So we use both face symbols here to denote all the vectors and the matrix, and plain text to represent scalars. So you see these are all the matrix and the vectors. So it's noted that the elements of X are all referred as state variables, X state variable, while the elements of Y are typically just subset of X. So the state variables that are measured, the measured variables will be the output vector to make the Y. And x, u, d, and y are normally functions of time, considering these are the dynamic models. So the time derivative of x is denoted by x dot, dx over dt, and the matrix A, B, C, and E are all constant matrix. Let's have a look based on the CSTR models how to derive this state space model. So we're familiar with the CSTR model already. It's a nonlinear model if we consider the concentration change of A and the temperature change of T, the dynamic terms. After we linearize it, we're able to get the nice shape. So this is the same model as we used before to describe CSTR. Because here Tc can vary with time. So the temperature Tc will vary with time, but the in-light concentration CAI, Ti, and Q and W are all constants. Okay. So based on this model, we want to express this in the state space shape. We just know that the physical models are the same, the dynamic behaviors are the same for the system, but transfer function models or state space models are just different type of representation, different mathematical representation of the process models based on the same set of physical laws. This state space shape will have a lot of nice features for controller design, so we want to use that to write the terms in the state space format. Okay, so this part actually is based on the textbook in the chapter 6 already. If you want to read the first edition textbook, the PDF, chapter 6, you can read the details yourself. Our goal here is to show the linearized CSTR model can be written in the state space form. And we want to derive the state space models for the two cases. First, both CA and T are measured. So we call that measured variables are defined as Y. So if we have both CA and T are measured, what is our state space model? And second, if only T is measured, what is the format? Okay, so the linearized CSTR model we have previously shown can be written in this vector matrix form. If we compare, this is the chapter 6 example. If we compare this format to this one, we just write in different equations or matrix, just combine these two terms together and use a matrix of all the coefficients grouped together as a matrix to describe the process. But if you see the dynamic function dCA prime over dt equals A11 CA prime plus A12 T prime, because it's a matrix operation, plus this is 0, so it's just these two terms summed up. That's exactly the same as this first equation to describe the dynamics of dC prime A. Well, for time, for dt prime over dt, again, this is written in the matrix form because the CA prime and the T prime are the same as the variable here, so it can be written in the matrix form. And there's this additional term with respect to TC prime with the coefficient of B2. Okay, so this is a general state space model. If we say both T and CA are measured, then we have this Y, the measured vector, to be exactly the same as X. So this is the second equation, Y equals X. If we want to write in the state space model, then C will become just an identity matrix because Y equals identity multiplied by X. If we recall matrix operation, so this I denotes a 2 by 2 identity matrix because X has the dimension of 2 as well. X is a variable of 2 by 1, vector of 2 by 1. Therefore, this I should be 2 by 2 identity matrix. And A and B are defined in the same format. Okay. And secondly, if we only have temperature T measured, then the output vector Y, it only has one variable within, that's the temperature. It becomes a scalar then, so Y equals T prime. And here C is a row vector then because Y equals CX, if we recall the state space model, right? Y equals CX. So if we have both concentration and temperature measured, then the second equation becomes Y equals X. If we only have the temperature measured, then this term becomes Y equals T prime. So the C becomes a row vector. The first term is 0 because the concentration is not measured. Only the second term is 1. The temperature is passed to the Y as a scalar. So we know that the state space model for this example has the disturbance term to be 0 because it is not included in the model originally. If we further suppose the phase composition and phase temperature to be the disturbance variables in the original nonlinear CSTR models, then this linearized model will have two additional deviation variables, CAI prime and the TI prime, to be consider the deviation terms, to consider the disturbance. Alright, so this is a quick overview of what is state space models. You just need to remember this specific shape because it's so useful if you want to do controller design or advanced control theory study. Just keep this X dot and Y, what's the equations here in mind for further study. Okay, so that's e-learning for today. You can send me any questions if you have. See you in class next week.